Now we are going to Germany to learn more about quality control and optimization with a smart metal part. How to add information to a blank and creating potentials for process control in the forming press. And I will now hand over to Johannes Weingarten, Chief Technology Officer at evopro Systems Engineering.
Hello, all together. And thanks a lot for the introduction of me and my presentation. I will right now start. I want to talk about quality control and optimization with a smart metal part. How to add information to a blank and creating potentials for process control in the forming press. We heard a lot of things about sensors and data, collecting data today, and my presentation that I will now give should give more information on how we can get the data, how we can in practice can achieve the data, and why we should why we have to get the data. To first start, I want to ask the question: what is the problem in the metal forming about quality? So the requirements to especially skin parts, when we talk about the car industry, are the most complex ones with regards to surface quality, geometrical tolerances like shape and robustness. The typical problems are cracks and thinnings, like you can see here, corrugations that you can have, and spring break. Of course, there will be a lot of other things that can be, but I do not have time to give you all the different examples. To achieve all the requirements, a long training phase is done, beginning with the right material, with a good panel cut, and with the right parameters for the deep draw process, which then in the end leads to a series production. So normally you have some when you have this training phase, you'll have some loop back for reconfiguring the deep draw process, or reconfigure the panel cut, optimize the cutting shape, perhaps also optimize the material type. But then somewhere at the end, the series production starts, and then this, let's say, very deep training phase is done, and then you have to cope with that. The critical point always is the deep drawing process. So if in the series production every incoming parameter is like the ones that training phase was performed with, the result will be good. What happens if there is one incoming parameter changing? Even worse, if there are more incoming parameters changing. So if you have some influence in the process. So without any knowledge about the incoming parameters, there's no possibility neither to act before an issue arises, nor to act in the right direction to prevent from getting an issue. I want to first talk about the control algorithm approach. I think this is quite used to everybody. A typical control loop. So you have the controller, you have the regulating value, which then influences the control system. Then you have the output, the control value itself. You have a loop back, and then you have the reference value, so the requirement that is coming in. And the difference between the reference value and the control value gives you the control deviation. Of course, you will have disturbances in the control system, and these disturbances always will lead to this deviation, and then the controller can act on that deviation and go back or try to compensate this deviation. When we now try to mirror this algorithm approach to the real process in the press shop, we would have the deep draw process here as the control system. Of course, we have the achieved quality at the output, which is then looped back. Then we have the quality requirements that are coming in. So when we just subtract both, we get the deviation, and the deviation might be a crack, a thinning, corrugation, or a spring back. The controller, let's stay the same. With the right control algorithm, then you can have the adjustments on forming speed, force distribution, spot oiling, or tool distances. Still, you have the problem that if the disturbance about any material change, for example, for the oil film distribution, or the sheet thickness, or surface roughness, material strength, or the preceding process parameters, they will appear after the control. Means that you still have a loss in quality, and then you have the possibility to compensate it. What if you would be able to move the knowledge about the oil film distribution, surface roughness, all these topics to the controller? Then you would suddenly have the possibility, before the quality is getting down, to control or to adjust the adjustment tools with the right control algorithm, with the knowledge about these things. So when we talk about the forming press, we have a lot of stacks that are delivered to the forming press, to the front of line, and then these stacks are being processed. What do we know currently in the current process about these stacks? So there might be the cutting time, the cutting machine, the material type info, and some blank type info. But that's mostly all of the information that we have within one stack. So there might be 500 blanks on each stack. But that's all of the information. So there's no position-related information. What we now would need to be able to influence the control algorithm would be, for example, the oil film thickness, the mechanical properties, the surface roughness, the sheet thickness. These are material properties, material-related values. Of course, we also have process-related values like leveling information from the stamping line, from the coil blanking line. We have the weld seam detection. So normally there are a lot of coils running around the world which are welded together. So you always have some position where there might be changes in the material parameters, and of course something like the brush cleaning. So that there exist different possibilities like wipers or washing machines. So these are all process influences that can be changed by the worker at the coil blanking line, which also influence the incoming parameters of the forming press. What else would be very interesting to have are the blank stacking positions, together with the stack storage surroundings. What does it mean? If you think of oil film thickness and the oil film distribution on each blank, when we assume we have a stack with 500 blanks stacked together, and this stack is going to the storage for 1 week in a warm summer week with 30 degrees outside, we can think of that the oil film distribution on the uppermost blank will be different to the oil film distribution on the lowest blank. So it is extremely important to know where the blank was located in the stack before it is unstacked or destacked in the forming press. How do we add the material and process information? So this is just a schematic of a standard stamping or a standard coil blanking line. And of course, there is one interesting thing how we can achieve the material information. And this is about the smart coil. The smart coil is it's a technique where the coil vendor they have a lot of measurement parameters because they have to fulfill the requirements for the coil material, and therefore they have to measure to be sure to be within the range. And on this coil, there is a barcode every meter, for example, and by reading out the barcode and then having some cloud interface, for example, to the coil vendor, you can get a lot of different measurement values from the coil. So, for example, it's the mechanical properties, the strip thickness, the roughness. The oil is a bit different because the oil will redistribute, so it doesn't make sense to get the measurements from, let's say, 5 weeks ago before the coil was shipped. So there is still some need to have measurements inside the line. So this is the other example, or the other method, to have inline measurements. The big disadvantage of the smart coil is that there's currently no standard to get the smart coil or to get the data with the smart coil, and there's not every coil vendor will have the possibility to print these barcodes and to deliver these smart coils. So the big advantage, of course, it's also a big invest, is to have the measurement machines in line of the coil blanking line. So you can measure the mechanical properties, you can measure the surface roughness, you can measure the strip thickness, and of course, the oil film thickness can also be measured. All these measurements then are combined with the strip position and the coil ID, and so they can be stored into a database, a cloud-driven database, for example. Also, as described before, the process parameters are very interesting. If you think of you have a weld seam, you want to know where the weld seam was in the strip. Other example is the leveling. If the operator is changing some parameters at the leveler, this could also be an interesting parameter for the later forming of the parts. And of course, as defined before, the blank stacking. This is can be done within the coil blanking line. Here you can also get the stacking position of each blank, so it is clear which oil film distribution at which position of the stack was applied. This is the data visualization, how this could look like in the forming press. So you have the strip and you have the distribution of different values like zinc layer or oil film thickness, things like that. Now we have a stack with a lot of different material or values from different measurement systems, but we still do not know when the part or when the blank is coming into the forming press, which part is it? Is it the first part? Is it the last? Of course, normally, if you strictly in the production process follow the stacking and unstacking position, there would be it would be possible to have a virtual tracing, but of course, as the real world looks like, it will not always be like this. So there could be a stack that could be restacked, so that the complete sequence is changed, and therefore it's quite important to have an identifier on each blank. So there could on the one side be the Eurofair barcode. This barcode has some disadvantages because It must be applied on all coils, of course. It must be placed with an interval which is smaller than the blank length. It must be placed left and right if the strip is cut longitudinal. It will vary in the position on each blank, of course, and it is washable, so it will disappear before the part is painted. Another possibility would be to make a laser marking, a laser engraving on each blank. This is more cost intensive, but this laser mark is staying through the whole lifetime of the blank, and yeah, it's not washable, and you can define the exact position with every part, so you will always have the same position of the laser mark. Yeah, together with all the material properties, also this marking is stored, and with this combination, with the mapping of the additional data or of the complete data to this code, it's possible now to identify a single blank in the destacker before the forming process is done, and to get all the information for the blank. This is how it could look like in the forming press. So to make the data available, yeah, there must be something to read out for example, the laser marking or the barcode from the Eurofair, and then you can have a visualization where you directly see in real time what are my material parameters about, what are the process parameters about. Of course, when you have identified each blank, you can add a lot of different information, like the cross brush, like the spot oiler, like all the different configurations from the deep draw stage. And yeah, what is missing still is the output quality. So to get the closed loop, we need to have the quality result. So there's on the one side, of course, a manual feedback through the worker. That's yes. So the log entries, issue description, it could look like this. So there could be an app where you have the part available, and you can just enter the issue, the defect that you notified. On the other side, there do also exist automatic feedback through end-of-line measurement systems. So like from Zeiss or Steinbichler, there are systems. There are also a lot of systems in the last years coming on the market about this shape measurement. And what else is possible is an automatic feedback through an inline measurement system. I want to show some short video just that you can see how this could look like. Now there is a camera system directly on the robot, which is then detecting quality while the part is transported from one stage to the other one. I just want to add one last topic when we think of laser shapes, because there's an interesting thing about notifying quality issues. When you think of you having a line like a characteristic shape, like a straight line, with a reference to the blank shape, and you have a hole that is stamped within the forming stage. So this has the reference to the 3D shape, and then you measure the distance, the smallest distance between the center of the hole and the line. You will have the direct result of the drift of the positioning of the blank when it was entering the first push and pull stage, and you have a direct feedback about the quality, because if you think of a displacement, then the blank holder will not work very proper anymore. Okay, so determining dependencies and control and create algorithm for closed loop control. The vision is the automatic control of the forming press for achieving a continuously high quality independent from the incoming influencing parameters. The task that we have to do is we have to learn from the smart metal part and indicate the dependencies between input and output. And the benefit, of course, is the increasing the amount of quality parts and decreasing the amount of defective parts. Thank you for listening. And as a company, we are working since 2010 on the topic of data mining in the press shop. And if you want to know more about the technical realization and the idea behind, you can just visit our websites like the evotrack, evoview, and the evopro website. Thank you.
So thank you very much, Johannes, for an inspiring speech. And I think we are all very eager to ask you more. But we don't have to only go to your homepage. We can also go to the Q&A session right away here. So I will now leave over back to Ingela.